So we left off in 4.3 talking about the power rule, we talked about what to do with the sum or difference of functions, and we talked about the product rule. So we have two operations left. We have the quotient rule, so with division, and then we have what to do with the composition of functions. Our quotient rule can get tricky. There are a lot of moving parts here. But you can probably tell that if I'm dealing with a quotient, obviously I'm dealing with some sort of division. So if my u and v are still functions, it's kind of how we typically define our functions when we write these rules. My u and v are functions. I'm going to do this. Everybody is still going to get a turn to get derived. But this time it's got to be in a specific order. So that's the wrong color. So I'm going to do v times u prime, and I'm going to subtract u times v prime, and that's all going to get, that should be v prime, not v squared. I'm thinking ahead, because that's all going to get divided by v squared. So I have vu prime minus uv prime, and it's all divided by v squared. Of course, this comes with the catch that v cannot be 0. There are a whole bunch of tricks to learn this. I just had it drilled in my head by rote, which is never the most effective way to learn it. But one of the ways, maybe I'll use a totally different color. Sure. If we kind of consider this the function up high and the function that's down low, we get this kind of like sing-songy rhyme kind of thing. And I can say this. I can say low d high, high d low, and we're going to divide by the square. Maybe I can spell right. Divide by the square of what's below. Right, so we get this kind of sing-songy rhyme. We get this low d high, high d low, divide by the square of what's below. And it helps really keep the term straight. Hopefully it works for you. If not, just completely disregard it and find something that works for you. So low d high, high d low, divided by the square of what's below. And you can kind of see that right here. Right, low d high, derivative of the higher function, the one in the numerator. High d low, derivative of the lower function, the denominator. Divide by the square of what's below, that lower function again. All of our tips from the product rule are going to come back into play here and be really helpful. So once again, I want to identify my u and my v. And I'm actually going to call them that, u and v. And just as before, I'm going to go over and do some side work. So u is x squared plus 5x plus 6. And if we look at my formula, you can see that I need a u prime, so I should probably find that. I'll get 2x plus 5. And my v is 2x plus 3, and again, I know I need v prime, so I'm going to find that, and I just get 2. Well, now I've got all my pieces, I can plug it right in. As always, kind of starting in general. Actually, maybe I'll shuffle things around here so I have some space. Oops. So I'll do my side work below instead. So I have my, I'll just copy it over for the sake of time, for the sake of not having to watch me rewrite this again. I've got my formula, right? Low d high, high d low, divide by the square of what's below. So I have all my parts, and I'm just going to plug them in. So v is 2x plus 3. U prime is 2x plus 5. U x squared is 5x plus 6. And v is 2. V prime is 2. And that all gets divided by v squared, 2x plus 3 squared. And I'm going to need to simplify this just a little bit. So let's FOIL, get 4x squared, 10x and 6x is 16x plus 15. This, just distribute the 2, 10x minus 12. We'll actually leave that denominator alone for now in the hopes that maybe I can actually eliminate part of it. So let me move my other example down a lot so I can just finish simplifying this. So I'm left with 2x squared plus 6x plus 3 divided by 2x plus 3 squared. I would be content with you leaving it like this unless you think it can factor out. So let's see what happens here. So we would normally need factors of the master product here, factors of 6 that add up to 6. 1 and 6, 2 and 3, this isn't going to happen. So this does not factor. We can leave it exactly the way it is. So here is my derivative. So all of the tips I talked about when we talked about product rule apply. Do your work out on the side. Get all your pieces straight and organized first. Work neat, work organized, copy down that original formula to help you out. That's exactly what we did here. Copy down the original formula, do your side work, plug in where appropriate. So let's try another one. Maybe I can move this back up. I can give myself some more room. So x cubed divided by 2x squared minus 1. Same thing first. Let's identify my u and my v. And do my side work, which for this example, just for the sake of space, again, I'll do below instead of off to the side. So u is x cubed. Of course, my power rule tells me that u prime is 3x squared. V, of course, is 2x squared minus 1, so its derivative is just 4x. And I've got all the pieces I need. So I'm going to copy down my quotient rule again. Where is it? There it is. Let's take this with me again. And I'll plug in where appropriate. So V, U prime. You can already tell that this is going to simplify much nicer than the last one did. U, V prime. That's all going to get divided, almost said derived again, by V squared. So keep the color right. 2x squared minus 1 squared. And again, let's just leave that alone for now. I'm really just trying to see if there's anything I can do at all to simplify this. So I get 6x to the 4th minus 3x squared minus 4x to the 4th divided by 2x squared minus 1 squared. I get 2x to the 4th, 3x squared, 2x squared minus 1 squared. Is this going to simplify? Probably not. All I can take out in the numerator is an x squared, which isn't really going to help me simplify much at all. So I would stop right there and say that my derivative is this quotient right here. So that's the quotient rule. Again, the more organized you stay, the better you will be. Now we're going to flip things kind of on its head here with the chain rule because there's no great way to organize this, no trick in terms of little rhymes like we have for the quotient rule, but we're dealing with composite functions. And if you remember with composite functions, I'm dealing with some kind of function within a function, right? F of g of x. So if I'm going to derive my composite function, so I have f of g of x then here's what I'm going to do. I'm going to work my way. I'm going to work from the outside in. So I'm going to start on the outside, and here's what's actually going to happen. I'm going to take f prime of g of x. So I'm going to derive what we call the outermost function, but still write it in terms of whatever's inside. You'll see when we do an example in a minute. And then I need to work my way in. So we can almost think about it like peeling away layers. We can almost think about layers. So I'm done with f. I've already derived it. So we're going to deal with g. And the first thing I need to do is derive that, g prime of x. Theoretically, if we were to have more and more and more functions, we would just keep doing this, pulling back layers, deriving every time. So this is my chain rule. So just to show a small example of that, if I were to do like x plus 2 squared, if f of x is x plus 2 squared, and I want to find its derivative, I'm going to work from the, like I said, from the outside in. So if I look at the big picture, the first thing I encounter is this power. So for the time being, we're just going to treat this inside piece like it's one succinct variable. So I'm going to do this outermost step 2 times whatever's inside, and I lower the power. That's just my power rule. Right? My outermost function is just something squared. And of course, its derivative is to take the power and lower it by 1. That's all that is. That's all it's saying. Cool, so I'm done with that. I want to highlight instead. I'm done with that. We can get rid of that layer and start thinking about what's left. Well, what's left? That inside piece. What's the derivative of x plus 2? I'm going to use my power rule again, and it's just 1. So my chain rule, final answer here, my derivative, is 2 times x plus 2. Working from the outside in. I had a teacher that, if you know like the Russian nesting dolls, or like those toys for like little kids that have like the cow inside the chicken inside the pig, he kind of taught it that way. So every time we would do a function, he would remove one of the Russian nesting dolls, or like the pig on the outside, and expose the cow in the middle, and then remove the cow and expose the chicken. And it will all sound better if I actually had one to show you, but I don't. So here we go. End of tangent. Let's try some examples. So here we are with the square root of 2x squared plus 5x minus 1. We have a function within a function, right? I've got this polynomial function inside my square root. We don't have a square root rule, but we do have a power rule, and we do have a way to rewrite this as a power. So let's start by doing that. So always start by rewriting as a power if you can. Right? Square root is the same as a power to the 1/2. Well, now this isn't something that I know how to work with. We're going to deal from the outside in. So if I look at the big picture again, right, my outermost function is that 1/2, is that something to the 1/2. So if I take my derivative, I start with that big picture. It's just a power. I can use my power rule. So it's 1/2 times that whole thing, lower the power by 1. Right, if I were to treat this inside piece as just, my inside piece as just, say, x, just like a single variable, that's just the normal power rule, and it still is. It still is. So I'm done with the square root. I can ignore that piece, and we can look at the middle. What's left is this polynomial here. Same deal, it's just the power rule. So I have 4x plus 5. If you wanted to simplify this, you could. I'm okay with leaving it exactly as you see it there. But if you really wanted to rewrite it, you could write this as 4x plus 5 over 2 times, the square root of 2x squared plus 5x minus 1. Just kind of manipulating my exponents. It's the same deal with g of x here. So with g of x here, same thing. I'm going to start by looking at my big picture. What's on the outside? Just that power of 4. So if I look at my outermost piece, right, this comes down. I treat it like power rule. I'm going to leave whatever's inside alone. Cool, done. Let's look at whatever's left over once I'm done with that layer. I'm left with this 2x plus 5. Well, derivative of 2x plus 5, just using my power rule again that we've talked about, is 2, which in this case I should simplify because it's relatively easy to do so. It's pretty easy for me to multiply the 4 and the 2 together, so I'm just going to do that, so I'm done with my derivative. So that up to this point is all of the rules that you need to know for all of these problems that we're going to talk about. All of the things you see in calculus moving forward come back to these big rules: power, product, quotient, and chain. And of course, sum and difference are in there too, but we know at this point just to go term by term. The problems that we've seen before are still fair game. Everything that we've already done is fair game. So here, right, this tangent line problem that we've seen before, except maybe I should actually write this as if it's a function. Now we can deal with more interesting functions. So find the equation of the line tangent to x plus 1 over x minus 3 when x is 2. So just like when we started dealing with these, we're going to start by dealing with point-slope form. I have a point, almost, and I need to find the slope. Well, easiest thing to do, if x is 2, I can plug in x to my function and get y. 2 plus 1 is 3. 2 minus 3 is negative 1, so y is negative 3. So great, I have a coordinate point now I can use in my function. The other thing I need is the slope. And remember, the slope is just going to be equal to the derivative of the function evaluated at that x value. So I have to find the derivative of the function. Well, if I look over here, notice I'm given a quotient. So I'm going to use my quotient rule. Right? I'm going to identify my u and v. We'll do some side work here, right? U is x plus 1, so u prime is just 1. V is x minus 3, so v prime is just 1. I can use my low, right? Low d high, high d low, divide by the square of what's below to solve this. So y prime is, looks like x minus 3 times 1. I'll just write it for the sake of completing it. X plus 1 times 1 divided by x minus 3 squared. Let's just reduce this a little bit to make it easier to deal with. I'm going to have negative 4 over x minus 3 squared. And if I evaluate this for when x is 2, I get negative 4 over negative 1 squared, so I just get negative 4. There's my slope. I'm going to come back to my point-slope form, of course, and I've got all the pieces I need. So y plus 3 equals negative 4, x minus 2, and I'm left with, this would be plus 8 minus 3 is plus 5. So here is the slope of my tangent line. So these problems are still valid. They are still fair game. We're just learning how to deal with bigger, more interesting functions. The last piece I want to talk about is if we start thinking about derivatives beyond just the first derivative, just f prime. So we can do that. We have notation that allows us to do that. I really just keep adding apostrophes, right? If you notice, I've got f prime of x, and we've also learned this dy by dx notation. This is, of course, my first derivative. I have my second derivative, f double prime, right? We would read this as double prime. And then my second derivative. The reason we have these two notations, by the way, is because there's a dispute over who really invented calculus, whether it was Newton, Isaac Newton, or a guy named Leibniz. And one of them invented one notation, the other one invented the other. Nobody could really pick one over the other, so we kind of have both. And I can never remember who invented which, otherwise I would tell you. Um, so of course I have my triple prime, or my third derivative. And also here, of course, I have kind of my nth prime and my nth derivative. So if you ever see this notation at all in a problem, you know what we're dealing with. The reason we kind of switched to this, I don't know, this parentheses notation is these apostrophes for primes get really unwieldy, right? If I was even looking at like the sixth derivative of x, I'm not gonna do this. That's just a lot and it's confusing. And usually past 3, we just default to parentheses and numbers. So my final example here real quick. If here's my function 3x cubed plus 5x squared minus 1, and I want to find f double prime of x, I want to find the second derivative of x, I'm just going to go one derivative at a time. So power rule, I get 9x squared plus 10x, and I need to do it again. So double prime, second derivative, 18x plus 10.